Welcome once again to the Maths Jedi channel. This is another video in my A-level series. This one today, carrying on through with the logarithms topic, we're looking today at natural logarithms and graphs. So I've got a PowerPoint here which I'm going to take you through. If you're new to the channel, I really would appreciate it if you could leave a like. That will help out the channel a ton and just helps us sustain and keep it going. And I appreciate all the help and support that you're giving me on previous videos, and I would definitely recommend you take the opportunity to look at some of the other videos on my channel, particularly if you're new at this time. So looking at this PowerPoint, we're just going to take our way through some of the basics. Hopefully you've seen the previous videos on logarithms, because the start of this is really just to go through again the rules of logarithms, but this time with natural logarithms instead. So just as a reminder, here are the basic laws of logarithms that we went through on previous video. Just to take account of the basic rules, make sure you've got them covered. So just remember that if you're adding two logarithms of whatever base, as long as the base is the same, that would be the log of both of those numbers multiplied up. In this case, our logarithm is base e, the exponential function, and we call that the natural logarithm or the Naperian logarithm, hence the ln phrase. And you will find the button ln on your calculator, so just make sure you've taken account of that. When you are looking at the natural logarithms, just make sure that you are understanding about what this is saying. This is effectively the same index law that says if you're multiplying things of the same base, you can add the indices. That's effectively what this is in logarithm talk. When you multiply things of the same base, you can add the powers. Similarly, if you are dividing things of the same base, you can subtract the powers, and this is the equivalent logarithmic rule to that. So log a minus log b is log a over log b, log a over b. So just be aware of that rule. This one, we talk about bringing n down to the front. So it's not like differentiation, but it's a similar sort of effect. You're bringing down the power. This is a sort of same index law that says if you're multiplying something of the same base inside of a pair of brackets, if you're raising something of a base in a pair of brackets to another power, that's the same thing as multiplying those two powers together. So this is the logarithmic form of that particular rule. Again, natural logarithms here, so ln. And then finally, just making sure that you've understood that if we're doing a natural logarithm of e to the x, in other words base e, then we're saying that that must be equal to x. So log of e to the x must be x, because log of e is 1. So where you see these sorts of things being used, just make sure you take into account the fact that in the similar way to normal logarithms, i.e. logs base 10, you would normally be seeing situations where you could have problems such as this. So this is saying e raised to the some power is 8. So e raised to the some power is 8. Now remember that the logarithm, the natural logarithm, has got e as the base. So you could take logs on both sides, but this time we use the natural logarithm. So by taking a natural log of e to the x, we can use that fact from the previous slide to say this must be x. So in this case, x is the natural log of 8. Very simple. On the calculator, just make sure you've taken account of where the natural logarithm button is. Natural logarithm button is over here, and you see above that button you have e raised to the power also. Just make sure you've taken that into account. This problem here, very similar to some of the problems I did on previous videos, just with natural log with an e base. So again, you would take natural logs on both sides. So you take natural logs of what's on the left and natural logs of what's on the right. Just think of taking natural logarithms as a function, like any other function. You do it to both sides. As long as you do it to both sides, the actual arithmetic is preserved. So by taking logs of this left-hand side, first of all, you can see that it's log e raised to the power of 7x minus 4. Well, because log e is just 1, we're going to have 7x minus 4 here coming down to the front of the expression. So 7x minus 4 on the left hand side, and then log 6 is just a number. And that's what happens here. And it's just taking away and dividing through to find x. Simple. Similar to other problems, you've seen a problem similar to this in the previous video. This is multiple powers of e now, so e to the 2x minus 3cx. The easiest way of doing this is you could use substitution. So you could say let y be e to the x, and then this would be y squared minus 3y equals 10, and then you could go from there. Alternatively, you just solve it straight out by inspection, and this PowerPoint takes you through it by inspection, but you just have to be aware that e to the 2x is e to the x squared. To be honest, I personally prefer substitution. Just gets my head around it a bit better. So either way is fine, but just be aware you can do it in substitutional ways in the way that I did in previous videos. The key thing is when you factorize this quadratic and get to this particular solution, just recognizing you can't have an exponential function that makes a negative number. So this will not give you a value, but you can find a value here. Obviously, in this case, log 5, natural log of 5. And that's what this particular section is talking about. If you're given equations that have logarithms in them, remember this is saying the log base e of 8x plus 7 is 5. So this is the outcome. Remember, this is the outcome. E is the base. So this is saying e to the 5 equals 8x plus 7. So you can do antilogs, what we call antilogs. So 8x plus 7 equals e to the 5. You just imagine taking the antilog of this, so the log disappears, and then the antilog of 5 with the natural base is e to the power 5. From there it's quite simple. Now I do explain on the previous video how these particular problems work, making sure you've understood where the e base is and how you convert between different forms. Just be aware, of course, that with natural logarithms, the base is the exponential function, e. When we're moving into graphs, it's worth recognizing that there is a way of turning exponential functions into graphs that's important. So what we're going to do here is we're going to do different forms, just understanding how to work it through. So we're going to look at polynomial problems first of all. So suppose our original model was a polynomial one, so sum x to the power n. Now by taking logs on both sides, we can use the rules of logs to change this into this form. So what's happening here is I'm splitting up the multiple, so log a plus log of x to the power n, and then I'm also using that rule where I bring down the power to the front, so n log x here, to get that particular situation happening. And then you can see that this is actually a straight line graph. This is what, if we imagine this is the y form, so y here, capital Y. If you imagine this is m, the gradient here, there's some number multiplied by log x. This is capital X, so mx, and then the c, the intercept point, will be log a. So this is actually a straight line graph equation just written with logarithms. If we use the different axes as log x and log y, it would have an intercept point at log a, because c was log a here. The gradient would be n, whatever the power was. And then log x obviously is the x-axis and log y is the y-axis. And therefore we can convert a polynomial problem into a linear one. In a similar way we can do it with exponentials too. So here's an exponential problem. We can take logs on both sides. In a similar way to before, we can bring down the x power. We're creating a y here, log y. If we make that capital Y, if we said this is x, so capital X here, then log b is the gradient, and then log a is the intercept point. So here we go. So similar to before, we've got x and log y now, so not log x like this one, but x. That's because we just said x is transferable. The intercept point was log a, because we said that was log a, here the number on its own. But the gradient here, the m, will be log b. So whatever the gradient here will be log b. And again, we're just converting an exponential form into a linear equation. Let's have a look at a problem to see ourselves looking at that in action. Of course, the first thing to understand is what kind of problem we're being asked to do. So here's a typical sort of problem. It says the graph represents the growth of a population of bacteria over t hours. The graph has a gradient of 0.6, meets the vertical axis at 0.2 as shown. Scientists suggest that this growth can be modelled by the equation p equals ab to the power t, where a and b are constants to be found. Write down an equation for the line. Well, let's have a look at what's going on here. We've got some function of t, and there's log p on the y-axis, of course. We've got the intercept at 2. So we have to think about what the graph equation is going to be. Okay, of course, thinking through how you take logs on both sides here, we would have log p equals log little a plus t log b. So t log b. So log b here is going to be the gradient, and log a, log little a, will be 2. So that's worth mentioning as well. So we know it's going to be p equals 2 and then b to the power t, whatever t is. Here in this case, because we know that the gradient is 0.6, we've been told that in the question, we're writing log p equals 0.6t plus 2. So that's y equals mx plus c form, but of course the intercept is 2 and the gradient is 0.6. Working our way through the answer then, we can work out what's going on, because we can take the logs as I just mentioned and start working our way through that. We knew that log a was 2, that means a must be 100. So how is that the case? Because log is base 10, if we're not told another base. So 10 to the power 2 is this outcome, 10 to the power 2 is this outcome, 10 squared, that's 100. And then log b is 0.6, so 10 to the power 0.6 is this outcome. So 10 to the power 0.6 is b, so 3.98. So that's the gradient, 3.98. And therefore we can then work out the meaning of the constant a in this case, because we can use those methods to work that way through. So a gives the initial size of the bacterial population, in other words, bacteria at time 0. So you start with 2 and then see how many you've got over time. And then obviously you've got the 2 different values here. So we can go back to our original equation and start understanding what that original equation would have been. It would have been 100 times 3.98 to the power of t. Here's another one, similar problem. This is talking about different populations in different cities and districts, and be aware that London is number 1 but has been excluded as an outlier because obviously it's very, very large. The relationship between the rank and the population can be modelled by the formula p equals ar to the n. So we're going to work our way through and just understand what's happening here. So draw a table giving values of log r and log p. So we just need to r and p and log p. So it looks something like this. So we just gone through with a calculator and worked out log base 10r, log base 10.2, sorry, log base 10.3, log base 10.4, log base 10.5, log base 10.6. And then log of p. So that's what these are. So log of 1,000,006 obviously. Log of 730,000 and so on. Then it says plot a graph of log r against log p using the values from the table and draw the line of best fit. So you just would draw a pair of axes. So what would the pair of axes look like? Well, log p would be the vertical axis, and log r would be the horizontal axis. In this case, we have a dropping gradient. You can see once you've plotted the values, you draw a line of best fit through those points, or as close to those points as possible. You'd need a bit of graph paper to do it effectively, but it looks something like that. And then use your graph to estimate the values of a and n to 2 significant figures. Here's where you need to use a bit of logarithmic calculation to work out what's going on. So if you took logs on both sides, you would understand that you've got log of p equals log a plus n log r. So in this case, we've got log p as being the axis here. Log a would be the initial point here, somewhere between 6 and 6.4. Okay, and then you've also got the fact that you've got n log r here, and it would be that n, the power, would be the gradient of your line, so you'd have to do a gradient. So you see the gradient here, they're using the change in y over change in x. So the change in y over the change in x, they are using some points from their graph that they would have got by drawing it to work it out. So just be aware they'd have to have drawn the graph a bit more accurately than we've got here. And then they're getting C 6.2, reading from the graph, said it was somewhere between 6 and 6.4. You can't really tell from this sketch, but obviously you'd read it from the graph if you had graph paper. And then you have to interpret what these values mean. We knew that log a would be the intercept point here. That means that 10 to the power of 6.2 is this outcome. That's what they're doing here. So 1,600,000, and then n would be the gradient in this case, so n is minus 0.67. Right, time to do some questions from the book now. So it's well worth us just trying to explore some questions for the book, just make sure we've got ourselves understanding of this. Okay, so here we are on page 327, exercise 14G. Just having a look at a couple of these questions to start with, just to give yourself some practice and some just useful sort of pointers for this. So we're going to go through a couple of these questions just to see what's going on. So again, I'll try and go through the hardest ones. You can have a look at the rest. But yeah, well worth you having a look and seeing if you can go through some of these for yourselves. So I'll look at E and F here, just to make sure you've got yourselves understanding what's going on. So E, first of all, is e to the 2x plus 6 equals 3. So what we're going to do start off is take natural logs on both sides. And again, because we're raising an e power to this, that effectively is just going to be 2x plus 6. And then natural log of 3 on the other side. Just for a moment, I just want to take a chance to make sure you've understood this, because I'm not really sure if you've quite got this yet. Just making sure you've understood it. This is log to the base e, so you have to remember this. So remember, in the rules of logs, we would have 2x plus 6 as the power. You bring down that power to the front, so you'd have 2x plus 6 log e here. So 2x plus 6 log e, those two things. And what is the natural log of e? So the natural log of e, that's worth thinking about. Well, remember, e to the 1 equals e. So we've got that, so e to the power 1. So the natural logarithm, so the log of the natural base e of e, this outcome, must be 1. So e is raised to that power, there's the power, to get the natural logarithm e outcome. So remember, log of e is 1. So because log of e is 1, that leaves you with 2x plus 6. I did skirt through it a little bit on the PowerPoint. I just wanted to take an opportunity to show you that, just so you had an opportunity to understand what was going on there. Right, back to the question. Very simple from here, of course. We just do 2x equals log 3 minus 6, and then x equals log 3 minus 6 over 2. Again, be really cautious with calculators, but do take your time with it. But it will do, these calculators are pretty good. They will give you a good representation of this as you're going along. So we're going to do log 3 minus 6. You see it here. Oops. Do that fit first then. And then divide it by 2. And then it's minus 0.2. So it's giving you answers in exact form. Minus x equals minus 2.45. 0.693856. Now, what does it mean by exact form? Exact form, it means give it like this. So give it as an expression, don't give it as a number, but I've written a number down just so you've got that as a reference. So when it says exact form here, make sure you've understood that it just means give you an answer that's an expressional form. I'll do the last one as well, just make sure you've got yourself understanding that. So the last one, we'll do this one a bit quicker. So e to the 5 minus x equals 19. Take logs on both sides. That gives us 5 minus x equals log 19. And then that means 5 minus log 19 equals x. And then from there we can leave it like in that form. So 5 minus log 19. Easy. Let's just take a look at the answers, make sure we've got ourselves understanding of that. So it's 14G. That's this one here. So we did the last couple, so I need to go down a little bit. Oops, where are we? Here we are. So 5 minus log 19, that's what we had. And then we had, well, it was we wrote it as log 3 minus 6 all over 2, but they've written it in a slightly different form, but these are equivalent forms to the answer I gave earlier, so that's absolutely fine. Okay, let's make our way through F here. So again, asking us to solve equations giving exact form. So we're going to anti-log both sides. So raise each side to the power to e to the raised to each power. So that's just going to leave us with this expression here. But I'm going to have e to the naught on this side. And e to the naught is 1. Anything to the power 0 is 1. And from there it's just a quadratic. So these two factorizable quadratic expressions. Two answers, 5 or 2. So 2f, 5 or 2. There we go. Brilliant. Let's trash my annotations, move down a list a little bit. We'll do one of these just so you've got a good semblance of what to do. We'll do E and F just so you've seen one of each type. So let's just take that. So 3e to the 2x plus 5 equals 16e to the x. Again, let's take everything to the same side first of all. I'm going to use a bit of substitution here, as I said earlier. It does help me get my head around it a bit. There's my substitution going on. So if I let y equal to e to the x, this is y squared, that's just y on its own. When you get to here, you can factorise the quadratic as normal, work your way through, and then work out your values of x. So that's the steps to go through. Just got to make sure you can factorise the quadratic effectively. So, just going through and factorising this. Sorry, I've gone a bit quiet. Right, so 3y equals 1, so y is a third, or y is 5. So y is a third, or 5. But remember, y was e to the power of x, so we just have to deal with that. Or e to the x is 5. So then we're going to have to do the anti-log both sides, log both sides. So x is log 3, natural log of a third. Or in this case, x is natural log of 5. Now, log a third is worth talking about. Oops, to wrap that out. Now, if you remember the second rule of logs, where you're saying if you take away logarithms, you can actually subtract them. Log of a third is the same thing as log 1 minus log 3, and log 1 is 0, so anything to the power of 0 is 1, so that's log 0. Log 1 is 0, so 0 minus log 3, so it's going to be x equals minus log 3, so I suspect the answers will say that in a moment, and then log 5, those two answers are fine. Let's just double check that. So it's where were we? 3e. So it's 3e, it gives it as log a third actually, or x equals log 5, but I prefer to say minus log 3 just because it's a little bit more simplified, but either way is fine, obviously. And then finally f. So again, I'll just write it out first. So same strategy really, just using a bit of substitution. So let y be log x in this case. We've got y squared equals 4, and then y plus 3 inside the brackets here. And that means that y squared minus 4y minus 12 equals 0. And again, that's quite a straightforward quadratic. So y minus 6, y plus 2 equals 0. So y is 6 or minus 2. That means that log x was 6 or log x is minus 2. Sorry, I can't squeeze that in, so let's just take that back a little bit. Minus 2. And then obviously you would have x here is e to the 6, or in this case x is e to the minus 2. So either of those answers would be working. So in this case we just want to see if the answer scheme has got both in there. So this is 3f. So e to the minus 2 or e to the 6. So that's what we have. E to the minus 2 or e to the 6. E to the minus 2, e to the 6. There we go. Right. I think I'll leave you to do the rest. I think the rest are worth having a look at. We will do another example in a minute of a graphing type problem, but the rest are for you to do. I would encourage you particularly to do number 7 because it's more of a problem solving type problem. And again, the answers are available at the back of the book, so you can have a look to see how you're getting on with those. I'd like to do some graph problems with you as well, so I'm going to just take this through and trash my annotations and show you some graph examples as well, just so you've had a bit of practice of all of the things I've went through on today's video. So these is from exercise 14H, so you can see 14H. It's a bit further through in the book, it's page 331. We are actually going to focus in on number 4, just to show you what the kind of thing that you might be expected to do. The questions tend to be a bit more scaffolded in the book, but I definitely would recommend you to practice a couple of these just to have yourself a good gathering of it, and we'll do some more when we come to round of the topic in a week or two. So let's just have a look at question 4. So you've got values of x and values of y. It's talking about y equals ab to the power of x. That's an exponential problem. Copy and complete the table of values x and log y, given your answers to two decimal places. So that's very straightforward. So I'll do that with you just to round it off, but just to give yourself a good start. So notice this is log y, so base 10 in this case. We've got 2 and 2.10 given to us, and then 3, and then I'll squeeze another one in. So 5, and then I'll do 6.5 down here, and I'll do 9 down here. Okay, so let's have a look. Calculator. Oops, get that away. So log of 424.4. Now these calculators, there's a little bit of a problem actually. These calculators are a little bit too complicated. So most calculators would have a log button. This hasn't got a log button. This is a log with a funny base button, so you just need to do log base 10. Most calculators assume it's base 10, but just you have to put the base 10 in. I suppose it's good because it gives you revision on that it is base 10, but just be aware. So in this case it's 2.64, 2.6, 3. We try and mirror the same answers here. I think the question does say give answers to 3 significant figures, or 2 decimal places in this case, so definitely worth going through and making sure you take account of that. 4097, 3.61, log base 10 of 30,763.6. Can be quite fiddly to do these. I definitely would recommend you do each one, just check each one, just make sure you've had a good amount of checking going on, because if you mess one of these up, your graph will be messed up and that can then cause you problems. And then finally, I just need to move this slightly over. So log base 10, 655,743.5, and that will give us 5.82. Okay, that's all the values. You'd have a table, that's fine. Then it's asking you to plot a graph of log y. Just make sure you know which axis is what. So log y would actually go on the vertical axis here, and then x only, because it's an exponential form. So x only across the bottom, and you'd plot obviously these points. So you'd have a bunch of x's, and you'd have to plot them all in and understand how they go. You can see it's going uphill, so it's going to be a line that looks a little bit like that. Okay, and it will intercept at the value the key value that you want, because obviously you'll be reading the graph off to find these values. So you'll be using your graph to estimate the values of a and b to one decimal place. So the gradient, first of all, so the gradient will be change in y over change in x. So this bit divided by that bit. So expecting something positive, that's going to be log b. Okay, for reasons I explained in the PowerPoint a few minutes ago. And then where it intercepts the axis, that's log a in there. So this gradient will be log b, and the y-intercept will be log a, but I'll leave you to sketch it and draw it. That's all for today's lesson. So I would definitely encourage you to do some of the others in this exercise and go through it at home, making sure you've had a good account of it. Just before I go, I'll show you the answers to number 4, so you've had a good understanding about what's happening. So number 4 here, and you can see here are the values. This is what the graph will look like when you plotted it, and as you would expect, it's gone through and worked out the gradient here using a triangle they've drawn, and understanding that it's log b. To get b, you have to do the anti-log, so it's 10 to the power of that number gives you this. And then obviously the log a would be where it intercepts. It happens to intercept at 1. So again, because it's log base 10, 10 to the power 1 is this outcome. So 10 to the power 1 is 10. So that makes a is 10. So don't forget to do that anti-logging bit at the end to get the a and b values out. Okay, I'll leave you try the rest at home. Definitely go back to the PowerPoint and have a look again before you attempt this exercise, because it is well worth you going through the theory first, making sure you understand the difference between exponential problems and power problems, because of course if you look at number 3, that's just a normal power problem, polynomial problem I called it in the PowerPoint, and this is an exponential problem. So polynomial problem, exponential problem, they're two different problems. The graphs are slightly different. So with one of the graphs you have both axes are logged, and with the other graph you have only one of the axes is logged, only the vertical axis is logged. Okay, I hope that's really clear. Thank you for watching for today. Hope to see you again soon. Bye bye.